Les microtubules sont des tubes d'environ 25 nanomètres de diamètre. Sur ces images, ils sont colorés en vert. Ils forment une structure très dynamique en étoile appelée astère, organisée à partir du centrosome. Les microtubules arriment et déplacent les chromosomes lors de la division. Ils positionnent les organelles dans la cellule. Pour cela, des protéines appelées moteurs moléculaires assurent le transport le long des rails des microtubules.
Der Unterschied von dieser Rekonstruktion zu einer tomographischen ist, diese basiert auf Mittelung. Ja.
Ce microscope électronique permet d'obtenir des images de microtubules à très haute résolution. Les parois des microtubules sont faites de la répétition d'une protéine appelée tubuline. À partir d'un ensemble de coupes très fines à travers une cellule de levure, il est possible de reconstituer l'organisation du réseau de microtubules de cette cellule.
And here there is one microtubule who goes the whole way to this tip. In this yeast cell, I think usually they say between 20 to 40 microtubules in a cell, and in a eukaryotic cell you would find much more microtubules, of course. When I have the microtubule oriented like this, I can model it. And so what I want to do is a 3D dimensional model of the microtubule cytoskeleton and see how the microtubules are organized in comparison to each other and everything else inside of the cell. You see how it created the line there? When I have all these lines put together, it becomes a model. And this model is now 3-dimensional. So you can see nicely the details of the cell, and on top you can see the models. For example, in red here, the nuclear envelope, and then you have the microtubules laying around it. I can vary this as much as I want, and then I'm doing, I can zoom in as well and look at specific details. For example, all the red ends is a capped microtubule end, which means it's a minus end. And all the blue balls, where I'm putting them, for example here, means it's a flared end, so it's probably a growing end of a microtubule. So what I do, I take these thin sections, I have a tomogram of each, and then I make a model of each, and then I join them all together. And so then I have a really large volume of the cell, and we can twist and turn as much as we want, and we can zoom in on details that we find interesting. So for example, if I take away the plasma membrane, it's easier to look at the microtubules. And then here, you can see how the bundles of microtubules are laying parallel to each other. And here in pink, I have modeled the centrosome. And you can see how the microtubules are laying straight on top of it.
Or is it not? Yes.
D'autres types d'observations, comme ici l'utilisation de lasers, permettent de travailler directement dans la cellule vivante. Il devient possible de suivre la dynamique des molécules et leur interaction à l'intérieur même d'une cellule.
On regarde dans une dimension, disons, d'à peu près un millionième de millimètre, disons là où la vie des molécules se passe. Et pour bien observer ces phénomènes, au fait, on doit aussi reculer dans le temps. Il faut carrément regarder dans des temps extrêmement courts. Donc le microscope que vous voyez ici est au fait désigné à observer des phénomènes sur des nanosecondes. But the cell is basically a shape in space. And the question is, how is spatial regulation of dynamic structures organized? So we want to know if the cell is capable of generating localized environment or environments that will actually direct the microtubule cytoskeleton in an asymmetric way, thereby actually directing shape. There's a local environment where this molecule is inactivated and therefore promotes microtubule growth. In other words, where the cell will move, the microtubules will grow into the extending lamellopodia. So in other words, a local environment is created at the leading edge of the cell that will actually direct the microtubules towards where the cell is moving. So now we have localized activity, not at the membrane, but on the chromosomes. A very similar principle applies to mitosis, where now what we need to do is actually direct microtubules towards the chromosomes in order to pull them apart. So again, we have a situation of asymmetric growth. Now this is a typical mitotic cell in metaphase, where we have a nice asymmetric growth towards the chromosomes. But again, if we look now at the state of this molecule that regulates microtubule growth, we can see here that again, it's in this floppy conformation, not interacting with tubulin exactly around these chromosomal structures. So basically a gradient around the chromosomes generates a steady state structure that will direct the microtubules towards the chromosomes. So the cell is now capable to generate a local environment by localizing activities on these macromolecular structures like chromosomes.
Le couplage entre les microtubules et les moteurs moléculaires est aussi un domaine d'investigation. Ces protéines motrices, appelées kinésines ou dinéines, convertissent l'énergie chimique de la cellule en énergie mécanique. Cela permet d'entretenir les mouvements au sein des cellules. Une source d'investigation pour les chercheurs. Dresde, Institut Max Planck.
For nanotechnology, we have turned the concept of the motor and the microtubules on its head. And instead of having the motor walk along the microtubules, what we're doing is we're having the motor move the microtubules. In this case, what we're doing is, or what you see here is the microtubule moving. It's moving in a trough that's about 1,000th of a millimeter wide. And because it's hitting the walls, it doesn't move outside of this area. We hope to be able to manipulate the direction and the locations of the motors such that we can manipulate small molecules in the nanometer range.
Et certains rêvent déjà à des micromachines actionnées par ces moteurs moléculaires.